Hello my friends and welcome back to KrossUSA channel. Today, we're taking you on an extraordinary journey through the world of precision machining. From massive 25-ton rotor shafts to intricate surgical skulls. Let's get started. Now this is what I call starting with a bang. We're looking at an absolute beast of a machine, the Boringer heavy-duty center lathe, stretching an impressive 12 meters in length and packing 195 kilowatts of raw power. This isn't your typical shop floor lathe, folks. This is industrial muscle at its finest. What we're witnessing here is the roughing operation of a massive rotor shaft, weighing in at 25.5 tons. To put that in perspective, that's roughly equivalent to 18 average-sized cars spinning between centers. The Boringer lathe handles this massive workpiece with surprising grace thanks to its robust bed construction and precision-engineered headstock. Notice how the cutting tool approaches the workpiece. We're seeing a heavy roughing operation where material removal rate is king. The carbide insert is designed specifically for heavy interrupted cuts, with a positive rake angle that reduces cutting forces while maintaining tool life. The coolant system is working overtime here, flooding the cutting zone to manage the tremendous heat generated by removing this much material. The spindle speed might look slow compared to what you'd see in a typical machine shop, but at this scale, surface speed is everything. We're probably looking at around 50 to 80 RPM, which translates to optimal surface footage for this diameter. The feed rate is aggressive, likely around 0.8 to 1.2 millimeters per revolution, because when you're moving this much material, time is money. What's particularly impressive is the machine's vibration dampening. With a workpiece this massive, any chatter would be catastrophic. The Boringer's design incorporates heavy-duty weighs and a foundation that probably weighs more than most complete machining centers. This is manufacturing on a truly industrial scale, where precision meets raw power. Switching gears from turning to milling, we're now watching the Waldrich Plano miller tackle a substantial face milling operation. This 110 kilowatt powerhouse is designed specifically for large format workpieces, and today's job is a perfect example, a 2000 by 1200 millimeter plate that demands both power and precision. Watch the face mill in action. We're looking at a large diameter cutter, probably 200 to 300 millimeters, equipped with multiple carbide inserts. Each insert is precisely positioned to share the cutting load, and the geometry is optimized for heavy material removal. The cutting speed appears conservative, but that's intentional. With a cutter this large, the outside inserts are already traveling at significant surface speeds. The workpiece is securely clamped to the machine's substantial table, which features T-slots and precision ground surfaces. Notice how the coolant system creates a continuous flood over the cutting zone. This isn't just about temperature control, it's also about chip evacuation. At this scale, chip management becomes critical to both surface finish and tool life. Here we have the VDF Boringer VDF 250T, a vertical turning lathe that represents German engineering at its finest. Vertical lathes like this one are particularly well suited for heavy, short workpieces, where gravity becomes an ally rather than an obstacle. The lathe shaft being machined is a critical component, likely destined for heavy machinery or automotive applications. What's fascinating about vertical turning is how it eliminates workpiece deflection issues that can plague horizontal setups with heavy parts. The workpiece sits naturally on the rotating table, held securely by the chuck jaws. Notice the tool turret positioning. The VDF 250T features multiple tool stations, allowing for complex operations without manual tool changes. We're watching what appears to be a combination of turning and facing operations, with the machine automatically indexing between different cutting tools as the program progresses. The cutting parameters here are optimized for both productivity and surface finish. The VDF's servo-driven axes provide exceptional control over feed rates and cutting speeds, allowing the operator to push the envelope on material removal while maintaining tight tolerances. Pay attention to the chip formation. Long, continuous chips indicate optimal cutting conditions. The machine's coolant system is precisely directed, and the chip conveyor system efficiently removes material from the cutting zone. This level of automation and precision is what sets professional-grade equipment apart from conventional machinery. Now for something completely different. We're stepping into the world of traditional craftsmanship at the Duchesne School of Forestry. where the art of bandsaw blade sharpening is still practiced with meticulous attention to detail. This might seem like a departure from our high-tech CNC world, but don't be fooled. Proper bandsaw maintenance is critical in any woodworking or metalworking operation. What we're witnessing is a masterclass in understanding cutting geometry, something that applies whether you're sharpening a bandsaw blade or programming a CNC router. The craftsman begins by examining the blade condition, looking for worn teeth, improper set, and damage. This diagnostic phase is crucial. Just like in CNC work, understanding your tool condition determines your approach. The blade is likely made from high-carbon steel or bimetal construction, designed for the demanding requirements of forestry applications. Watch the sharpening technique carefully. The file angle is critical. Too aggressive and you'll weaken the tooth. Too shallow and you won't restore proper cutting geometry. The craftsman maintains consistent pressure and stroke length, ensuring each tooth receives identical treatment. This is precision work that requires years of experience to master. The tooth set operation follows sharpening. Each alternate tooth is bent slightly outward to create clearance for the blade body. This set must be perfectly uniform. Uneven set leads to blade wander, poor cut quality, and premature wear. Notice how the craftsman uses specialized tools to ensure consistency. The final step involves checking the blade tracking and tension. Proper tension is crucial for accurate cuts, but over-tensioning leads to premature fatigue failure. This balance between performance and longevity is something every machinist understands, whether working with bandsaw blades or CNC tooling. This traditional skill represents the foundation of all cutting operations. Understanding how metal removes material, the importance of proper geometry, and the relationship between cutting forces and tool life. Welcome to the cutting edge of manufacturing technology. The Hermel C400 represents the pinnacle of 5-axis machining capability, and today we're watching it create something truly special. A detailed sailing boat from 1.4404 stainless steel for the die and mold industry. What makes this particularly fascinating is that we're starting with an additively manufactured blank using MPA, metal powder application technology. This hybrid approach combines the design freedom of 3D printing with the precision finishing capability of 5-axis machining. It's the best of both worlds. The Hermel C400's simultaneous 5-axis capability means the cutting tool can approach the workpiece from virtually any angle while maintaining optimal cutting conditions. Watch how smoothly the machine transitions between complex surfaces. There's no repositioning, no reclamping, just continuous machining from setup to finish. The material 1.4404 stainless steel presents its own challenges. It's work hardening, which means cutting parameters must be carefully controlled to prevent surface hardening that would make subsequent passes more difficult. The Hermel's advanced spindle and feed drive systems provide the precise control needed for this demanding material. Notice the toolpath strategy? The CAM software has generated smooth, flowing motions that minimize direction changes and maintain consistent chip loads. This is particularly important in 5-axis work, where sudden direction changes can cause tool deflection and surface finish problems. The boat's intricate details, the hull curves, deck features, and fine details would be impossible to machine with conventional 3-axis equipment. The C400's tilting table and swiveling spindle head work together to maintain perpendicular tool orientation to the surface, ensuring optimal surface finish and dimensional accuracy. This represents the future of manufacturing, combining additive and subtractive processes to achieve results that neither could accomplish alone. The Cut T30MC represents modern turning technology at its finest, and we're watching it machine a hydraulic coupling from 42 CRM04 steel, a material choice that immediately tells us this component will see serious service conditions. 42 CRM04, also known as 1.7225 or SAE 4140, is a chromium molybdenum alloy steel prized for its combination of strength, toughness, and hardenability. It's commonly used in high-stress applications like automotive drivetrain components, hydraulic systems, and heavy machinery. The fact that we're machining a 55mm by 105mm hydraulic coupling from this material suggests this part will handle significant pressures and mechanical loads. The Cut T30MC features VDI 40 tooling, which is a standardized tool holding system that provides exceptional rigidity and repeatability. VDI tooling eliminates the flexibility issues common with traditional tool holders, allowing for more aggressive cutting parameters and better surface finishes. Watch the hydraulic coupling system in action. This isn't just about holding the workpiece, it's about maintaining consistent clamping pressure throughout the machining cycle. As cutting forces vary, the hydraulic system automatically adjusts to maintain optimal grip without overstressing the part. The cutting operation showcases modern carbide tooling technology. The insert geometry is specifically designed for 42CR-MO4, with a coating that resists the abrasive nature of this alloy steel. Notice how the chips form. They're well controlled and evacuated efficiently, indicating optimal cutting parameters. The machine's spindle speed and feed rates are carefully balanced. Too fast and we risk work hardening the surface. Too slow and we lose productivity. The MT Cut's advanced control system likely includes adaptive feed control, automatically adjusting parameters based on cutting load feedback. This level of precision and control is what makes modern turning centers so productive. Every aspect, from the work holding to the tooling to the machine dynamics, is optimized for specific material and application combinations. This is where art meets technology in the most dramatic way possible. We're watching the Hermel C400, programmed with SolidCAM software, create a detailed human skull, a project that showcases the incredible precision and artistic potential of modern 5-axis machining. This skull represents one of the most challenging geometries imaginable for CNC machining. Every surface is curved, there are deep undercuts, intricate details around the eye sockets, nasal cavity, and dental features. This requires not just mechanical precision, but sophisticated CAM programming to navigate these complex surfaces without collision. SolidCAM's 5-axis capabilities shine here. The software has generated toolpaths that maintain consistent step-over distances across highly variable surface geometries. Watch how the tool orientation changes continuously. The spindle head tilts and rotates while the table simultaneously positions the workpiece, creating a ballet of synchronized motion. The cutting strategy appears to be a combination of roughing and semi-finishing operations. Initial roughing removes bulk material quickly, followed by progressively finer passes that develop the intricate surface details. The tool selection is critical: longer, smaller diameter end mills for deep cavities, broader cutters for open surfaces. Notice the surface finish quality emerging as we watch. This level of detail requires exceptional machine rigidity and vibration control. Any chatter or deflection would immediately show up as surface imperfections, but the Hermel C400's construction and control systems maintain micron-level accuracy throughout these complex motions. The eye sockets present particular challenges: deep, curved pockets with varying wall angles. The CAM software must calculate tool accessibility for every point, ensuring adequate clearance while maintaining cutting efficiency. This is computational geometry at its most sophisticated level. What's remarkable is how the machine handles direction changes so smoothly. Traditional 3-axis machining would require multiple setups and potentially dozens of different tool orientations to achieve these results. The C400 accomplishes it all in a single setup, eliminating setup errors and maintaining perfect part registration throughout. This project demonstrates why 5-axis technology has revolutionized industries from aerospace to medical devices. The ability to create complex geometries with unprecedented precision opens possibilities that were simply impossible just a generation ago. Here's something every programmer and shop owner should pay close attention to: a complete workflow demonstration showing how Edge Team utilizes EdgeCAM 12.5 software with the Mazak Integr platform. This isn't just about machining, it's about the entire digital manufacturing process from design to finished component. The Mazak Integr represents the pinnacle of multitasking machine technology. It combines turning, milling, drilling, and secondary operations in a single setup, eliminating transfer errors and reducing cycle times dramatically. What we're seeing is the EdgeCAM software managing this complexity seamlessly. EdgeCAM 12.5 features advanced CAM capabilities specifically optimized for multitasking machines like the Integr. The software understands the machine's capabilities and limitations, automatically generating collision-free toolpaths while optimizing for both cycle time and tool life. Watch the programming process carefully. The operator begins with the part model and quickly defines machining strategies for each feature. EdgeCam's feature recognition technology automatically identifies common geometries, holes, pockets, external profiles, and suggests appropriate machining strategies. The simulation phase is crucial. Before any metal is cut, EdgeCam provides complete 3D simulation showing tool motions, potential collisions, and material removal. This virtual verification prevents costly crashes and ensures first-part accuracy. Notice how the simulation includes not just the cutting tools but also the machine structure, chuck jaws, and tailstock. During actual machining, we see the Integrex's impressive capabilities. The main spindle handles primary turning operations, while the subspindle prepares for part transfer. The live tooling in the turret enables complex milling operations without part repositioning. This level of integration requires sophisticated programming, and EdgeCam manages it all automatically. The part transfer operation is particularly impressive. The subspindle extends to grip the partially machined part, the main spindle releases, and the part is transferred for secondary operations. This happens while other tools are being positioned for the next operation. True multitasking that maximizes spindle utilization. Quality control is integrated throughout the process. EdgeCam includes measurement cycles that verify critical dimensions during machining, enabling real-time process adjustments. This proactive approach to quality ensures parts stay within tolerance throughout the entire cycle. The finished component showcases what modern multitasking technology can achieve: complex geometries, multiple operations, and precise tolerances all accomplished in a single setup with minimal operator intervention. The Glisten Agilus 180th represents the future of gear manufacturing, a single machine that combines turning, hobbing, chamfering, and deburring operations in one integrated platform. This is efficiency engineering at its finest, eliminating multiple setups and handling operations that traditionally required separate machines. Gear manufacturing has always been a specialized field requiring dedicated equipment and extensive expertise. The Agilus 180th changes that paradigm by integrating multiple processes while maintaining the precision that gear applications demand. We're watching gear technology evolution in real time. The turning operation begins the process, creating the basic shaft geometry and preparing mounting surfaces. The machine's turning capabilities rival dedicated lathes, with precise spindle control and rigid tool holding systems. Notice the surface finish quality. This isn't just roughing, it's precision turning that creates finished surfaces in one pass. The hobbing process is where the magic happens. Gear hobbing is a continuous indexing process where the hob cutter and workpiece rotate in precise synchronization. The Agilus features a high-precision hob spindle with exceptional run-out accuracy and vibration control. Watch how smoothly the teeth are formed. Each pass of the hob creates multiple teeth simultaneously. The chamfering operation follows immediately, using specialized tooling to create precise edge breaks on the gear teeth. These chamfers aren't just cosmetic. They're critical for gear meshing performance and noise reduction. The machine's ability to seamlessly transition from hobbing to chamfering demonstrates sophisticated control integration. Finally, the deburring process ensures all edges meet specification requirements. Modern gear applications demand consistency, and any burrs or sharp edges can affect performance and longevity. The Agilus completes this operation with the same precision as the primary machining operations. What makes this truly impressive is the integration. Traditional gear manufacturing might require 4 different machines, multiple setups, and extensive work-in-process inventory. The Agilus 180th accomplishes everything in a single setup, maintaining perfect part registration and eliminating accumulated tolerances from multiple operations. we're concluding our journey with something that perfectly encapsulates the versatility and precision of modern CNC technology: one CNC Research Department's machining of a complete soccer ball. This project demonstrates that CNC machining isn't just about industrial components. It's about pushing the boundaries of what's possible. The soccer ball presents unique challenges that test every aspect of CNC programming and machine capability. The spherical geometry requires continuous 3-axis interpolation, while the surface pattern demands precise positioning and consistent depth control. This is computational geometry meeting artistic expression. The surface pattern creation requires exceptional precision. Each pentagon and hexagon must be identical in size and depth, with perfect transitions between adjacent surfaces. This demands not just accurate programming, but also exceptional machine repeatability and thermal stability. Notice the tool selection, likely a ball end mill sized to create the desired surface radius in the pattern elements. The step-over distance is carefully calculated to eliminate cusps while maintaining reasonable cycle times. This balance between quality and productivity is fundamental to successful CNC programming. The work-holding system deserves special attention. Machining a sphere requires secure clamping that doesn't interfere with tool access. The One CNC team has solved this elegantly, likely using a custom fixture that supports the workpiece while providing complete access to all surfaces. The finished result is remarkable: a complete soccer ball with precise geometric patterns, smooth surface transitions, and consistent surface finish throughout. This project demonstrates that CNC machining is limited only by imagination and programming skill.